Hey there everybody in quarantine land. Today's video is going to be a geometry video, and based on the pictures on the screen you can probably tell it is going to be a side-splitter theorem video. So let's get into the side-splitter theorem. Side-splitter theorem will always involve a triangle that has a segment drawn within it that intersects two sides of the larger triangle. So right here, this segment BC intersects ADE at B and at C. Another important point, that line, the segment that's drawn, has to be parallel to the base of the larger triangle. Otherwise, none of this works. So how do I know they're parallel? Well, these little arrows indicate parallel lines. So if you see these arrows or these little symbols, then you know those two lines are parallel. So we have everything we need to use the side-splitter theorem. And really, the side-splitter theorem is nothing more than what we've already learned back in junior high about similar triangles. And so let's look at the relationship that we really have here to try and make this make more sense. So we have two similar triangles from this figure. We have triangle ABC and triangle ADE. So we have triangle ABC is the smaller and triangle ADE is the larger. And those are similar triangles. If you remember back from junior high geometry, all you need to prove that triangles are similar is that two angles are congruent. Because if all three angles add up to 180 degrees, as they do, if two angles are congruent, then all three are. So let's go ahead and show how these are similar. First of all, we should know that both triangles have angle A in them, right? ABC and ADE. So that's our first step. Both triangles share angle A. Now all I have to do is prove one other set of angles are congruent. So remember, we have parallel lines. And remember when we learned parallel lines that were cut by a transversal? So if you had parallel lines cut by a transversal, you created alternate interior, alternate exterior, and corresponding angles. So, and they were all congruent. So if we look at this right here, BC and DE, and imagine they're extended, they're parallel lines. It's cut by two transversals. One is AD and one is AE. So the transversal AD creates angle ABC congruent with angle ADE. So those are our first sets. BC is parallel to DE. We have that relationship formed by parallel lines cut by a transversal. We have ABC is congruent to ADE. Now you probably can already figure out the other set of congruent angles or corresponding congruent angles. We have AE is another transversal that cuts the same two parallel lines, so it creates ACB and AED. So again, we have two sets of corresponding congruent angles, and let's mark them there. So now we've proven that we have two similar triangles, right? We've shown all three angles are congruent, so we have now shown that triangles are congruent by the angle-angle similarity theorem. So we're doing a side-splitter theorem. Why did I spend all that time showing you that these two triangles are similar? Well, what do we know about similar triangles? We should remember that similar triangles have proportional side lengths, and that is every single thing the side-splitter theorem says, right? So let's look at the side-splitter theorem, remembering that we already understand everything we need to know about it. So it says if there's a line within a triangle parallel to the base that intersects two sides of the triangle, it divides those two sides proportionally. All right. Now, it has two different relationships. It creates a part-to-part relationship and a part-to-whole relationship. And let's look at both of those. So here's a triangle, similar to the one on the last page. And so we have ABC is the smaller, ADE is the larger. We already know they're similar because we just proved it on the previous screen. And this says that A is to B as C is to D. So these little segments, these little side lengths are proportional. That's probably not what you're thinking about when you think about similar triangles. You're thinking about part-to-whole relationship. Okay? If we break these two triangles out, we would see triangle ABC with side, and I just made side A and side C here. And if we took the larger triangle ADE and broke that out, this is A plus B, right? Because we have A and B, so we'd combine those. So this would be A plus B, and this would be C plus D. So this is the relationship we're used to seeing. Okay, A is to A plus B as C is to C plus D. We're used to this one. This one is the new relationship. The A to B is C to D. But, you know, if part to whole works, part to part is going to work. That's how ratios work. So let's find a problem where we could use the part-to-part relationship. And it happens to be the first problem on that first screen. So we have a problem that says solve for x. It doesn't tell us anything about parallel lines, but I know that this line is parallel to the base because I have that little doohickey mark that says, hey, parallel lines. So I have a part 3, a part 2, a part x, and a part 3.2. I could use either. I could use part to whole for this. In fact, the last problem in this little video, I'm going to do one that you could do with part to part with part to whole. But let's make this easy. Let's do part to part. Let's set it up as 3 is to 2, right? We're going to say A is to B, so 3 is to 2 as x is to 3.2. So let's do that. 3 over 2 equals x over 3.2, or 3 is to 2 because these are ratios. So we're going to say 3 is to 2 as x is to 3.2. You remember from junior high days how to solve proportions, hopefully. We cross multiply and divide. So we're going to do 3.2 times 3 equals 2 times x. So now we'll have a nice equation. 3 times 3.2 is 9.6 equals 2x. Remember, when we have a variable on one side of the equation, we want to get it alone. It is not alone. There is a 2 with it. It is multiplied. The opposite of multiplying by 2 is dividing by 2. So x is equal to 4.8. Done. All right, let's look at another problem. So for this problem, I don't see little parallel marks, but you have to look at what they've given you in the directions. It says, given that segment DE is parallel to segment AC, that's what this little symbol means. These two lines that are parallel mean or indicate parallel lines. Segment DE is parallel to segment AC, solve for x. Okay, so I have what I need. I have the parallel lines within the triangle. I can use Side-Splitter Theorem. Now, for this one, I am going to use part to whole. You could use part to part. You could say, well, if this whole thing is 8 and this is 6 and this is 2, but then look what happens. This whole thing is 16 and this is x. This would be 16 minus x. Nobody wants to do that. So we are going to use the part to whole relationship. We are going to say A, this little segment here, is to the whole thing, right? Because I have A. A is given to me as 6, and A plus B is given to me as 8. Okay, you don't need to add 6 plus 8. This is already the entire side length. So that is going to be equal to x over 16. Remember, whole 16 is already given. You don't have to do any arithmetic. So let's set it up. 6 is to 8 as x is to 16. Cross multiply, and we will get 16 times 6 equals 8x. 16 times 6 is 96. We'll divide by 8 and get x equals 12. All right, easy peasy. We'll do one more. Now, this one I would probably set up as part to part. And you should set this up as part to part if you were going to do it. But I'm just going to show you that you could do part to whole. If for some weird reason you had to do part to whole, or somebody said, like your teacher said, oh, do part to whole because there's enough information, fine, you could do it. So if we use part to whole, we have to do some addition first. We're going to say 6 is to the whole. So we don't have the whole. We actually have to add these, right? 6 is to 6 plus 8 as x is to 12. So 6 is to 6 plus 8 as x is to x plus 12. See why I don't like doing this? 12 is not the entire length. It's x plus 12, right? So 6 part, 6 plus 8 whole. X part, x plus 12 whole. All right, so let's cross multiply. It's not as bad as it looks. All right, when we do that, we're going to get 6 times the quantity x plus 12. Remember, anytime you have two terms, you have a binomial in this denominator, you have to distribute. That 6 gets multiplied to both those terms. And then 6 plus 8 is 14 times x is 14x. So we have to distribute. See why we would never use this? You would just use part to part. 6 times x plus 6 times 12 is going to be 6x plus 72 equals 14x. Now we have x's on both sides of the equation. Now we don't have two different variables. They're still just x. X can't represent two different things. But what we have to do is get the x terms on one side of the equation. So we just take the smaller value, 6x, and we subtract it from both sides. You could subtract 14x if you really like negative numbers, but I don't, so I'm not going to. Subtract 6x from both sides, 72 equals 8x. Divide by 8, x equals 9. If you did part to part, you would get x equals 9. But there are some students that are like, I'm just going to use part to whole because it's what I know best. Sometimes, as in this case, part to whole causes a little more work. But if you're up for it, you can totally do it. If that helped you, great. If not, there's always student help available on my YouTube. You can send me a question. You can look for other videos. That's it for now. Until next time, stay healthy and wash your dang hands, huh?